Everything's waiting. Okay, and then we need to activate this for Marcella. Right, I think I pushed all the buttons that we need to push to get started. Welcome to Neuroccino on this Monday morning. Hello. It's actually quite exciting because last week we had a paper that we discussed, and Chris made a point about the measurement maybe not being ideal, and that there is new results about the dice coefficient that may make it, that may necessitate us looking different at that measurement. And he kindly volunteered to step in and present said paper this week. Evie is laughing. I did not force him. I just kindly asked. But also the timing couldn't be better because that paper just got published in Nature Methods, I believe, last week. So we were discussing the preprint, and now it's actually out in Nature. So I think this is a very timely and exciting presentation today. And Chris, if you want to share the link, thank you. And your screen, you can take it away. Thank you.
All right, so this paper, so it's been published last week in Nature Methods, but there is a paywall, so I used the latest version on Archive. I'm pretty sure it didn't change too much because you'll see that it is a big process. So it is called Matrix Reloaded, Recommendations for Image Analysis Validation. There is actually another sister publication with complementary information because it is a massive topic. And to tackle this massive topic, they gathered more than 70 experts in the domain of machine learning in medical imaging, and even more than the list of authors, because then they asked also the community for feedbacks, and they used what's called the Delphi protocol, the Delphi process. I didn't know about it. So I asked a ChatGPT to give me bullet points to summarize what it is. So the goal is to try to find what is the best way, like a standardized way to decide what metric to use in machine learning, especially in the imaging, the medical imaging domain, because as they explained, there's been some issues with the classic metrics. For example, the most famous metric is DICE, and in the paper, in this consortium paper, they explain that DICE, for example, cannot be used for every single problem that you have in medical imaging. So to find a standardized way to decide, depending on your problem that you're or your question that you're trying to answer with machine learning, they use this Delphi process where they have like a structure. So it's a structured method with several iterative rounds, with usually it's with anonymous answers, so people can reply really what they think, not like, oh, maybe I'm not an expert, so I shouldn't say this or that. So anonymous responses from the experts, and the goal is to converge on a consensus. It's literally the process, the Delphi process goal is to arrive to a consensus in the community, and they have a stop criterion, maybe like when the percentage of agreement on different parts of the question reaches a threshold, and then they decide what should be done with what they found with the consensus. And yeah, so to come back to the issue, the problem is that a number of papers, of publications, well, there are loads and loads of publications about machine learning in medical imaging, but we don't see very often these results used in actual clinical practice. And the point of the matrix reloaded consortium is to say that it is at least partly due to the misuse of the metrics that we use to validate the performance of these models. So first, you have to choose what problem you're tackling with your machine learning model. And it can seem a little bit trivial at the beginning, but you'll see that it is not that simple, because depending on the problem that you're trying to solve, you will have very different ways to validate the performance of your model. And so then it leads to poor metric selection that doesn't reflect anything useful for the potential practical application. And also you can not apply the metrics as they are intended. So it will also make your results not applicable in real life. So they have very nice figures to show what kind of problems you can have with your metrics. So the first one is if you don't formulate your problem correctly, if you're confusing object detection with semantic segmentation. So if you want to detect objects in a reference image, if you consider it as a segmentation problem, so you use the dice, basically it's telling you the percentage of overlap between the prediction of your model and the reference that you're trying to achieve, your target reference. And you see here that if you use the dice, the DSC, you would have a super high dice in this first prediction, but you missed 2 objects. So if your goal was to detect a certain number of objects or how many objects you have in an image, you're actually failing. But your dice metric is giving you a very high score. So, of course, when you're trying to apply the results of this model, it's not going to work because it's actually missing most of the objects. So, and you see that if your prediction was a little bit off the main object, but you were capturing all the objects, you would have a lower dice. So it's actually really bad because when you're validating, you're actually having opposite results from what you want. Another, I mean, that's a simple example, but that can happen in so many cases. Another problem is with the selection of the metric, where you could, if you select the dice again, the dice has an inherent issue with small objects because it is calculating a proportion of overlap. If your object is very small, you could detect it, but partially, and have a very low performance score. But in that case, you actually detected it. So of course, it depends on what is your goal. If you want to have an absolutely perfect overlap, there are different metrics that will help you with that. But if it's to detect at least the location of the object. You could be more interested in the center of the object or stuff like that. You will have to change the metric that you use. And the last big category of pitfall that you can have with machine learning is the poor application of the metric. And in that case, you take the example where you have a big data set but with only a few patients, but each patient has many images, 130. And you could think, oh, I will just average my performance metric over the images. But this is actually, that would give you a wrong score, because if the metric is performing, if your model is performing super well on one patient with a lot of images, that will skew your performance score, and you will think, oh, I have a great score of 80%. But if you average per patient, which makes more sense, because if the model is not able to capture, I don't know, if it was a lesion or something, you could have an easy lesion with patient 1, but a very hard one for patient 2 here. But because the patient 1 has more images, it would bring up the performance metric artificially. So what you want to do is to average it per patient and not per images. So to detect and decide these problems, they came up with a tool to formulate, to express your problem that you're trying to solve with machine learning. So you have, and they made a tool, an online tool, where you can you answer some questions. It's like a survey, and throughout the process, it will refine the definition of your problem and then advise you on what metric to use. Um, so um, yeah, so the goal is to the whole goal of the paper is to make a tool that will take into account the specificity of the problems to then choose better metrics that will be more adapted to the practice. So first the fingerprint, um, and then so you have to you choose your metric, then it will give you advices on how to apply these metrics. There is that they describe the whole process of selecting your problem. So you see that it inside is really complicated, but the process is actually pretty straightforward, because of course you're only going through one branch. You don't have to go through all the branches, but that's the process that they came up together with like more than 70 people. That's pretty impressive that they agreed on a structure like that. Well, that's why it took I think it started in 2020, and yeah, it took 4 years to publish that. And they have some examples of some problems that you want to take to pay attention to. Depending on the for example, here you have the importance of the boundaries. So are you really interested in very accurate boundaries to your segmentation, or you're more interested in the center of the image of the object that you're trying to detect? Because depending on what you want to do, it might not have the same importance, and then you need to choose the right metric to deal with the problem differently. What I can show, yeah, they have some more real life examples. So they classified the problems in 4 different categories, which they explain that it's all these problems can actually be under the classification task umbrella. They are just classifications at different scales. So from the top, you have the image level, where you're trying to get a performance. Well, you will have a performance for the whole image, so you will, because you want to have a prediction for the whole image. So here you want to see if the image, there is a malignant, the proportion of malignant cells you have, then infected, uninfected. And I think this one, it's the well, yeah, I don't know what it is, this part. But then if you're more interested in specific objects in the image, you will, of course, you will have different problems and you will use different measures. Then you have the object, but at the pixel level. So that's more the kind of things that I would do. The segmentation of objects in the image, and the just pixel level. So you want to see in each pixel the probability of something, here malignant or benign, and here the detection of the tools. And depending on these problems, you will use different metrics. They also wanted to make it modality blind, so it doesn't care what modality you're using, because the type of problem that you're trying to solve is similar in different modalities. Yeah, so what I said, they regard every problem as a classification task in that case. And an interesting thing is that they give you a recommendation for the metrics that you should use depending on your problem, but they also included some metrics that are not widely known, that could have benefits for your specific problem, that the community brought up during their consensus building. Um, um, yeah. Yeah, also the one thing that they advise is to use complementary metrics. So last week, I was criticizing the use of the dice score, and they had a very complicated model doing a lot of things, and the only performance measure that they were using was the dice. And as this paper shows, the dice has some pitfalls. That doesn't mean that you shouldn't use it at all, but that means that it might be better to add another measure to evaluate the performance of your model. And it's better to have several measures, because they will capture different aspects of the performance of your model. So they have a lot of yeah, they made a very structured process to formulate the problems. First you formulate the problems, you select the metrics, and also they give advice on how to use the metrics. One thing that I thought was interesting also, you can actually misinterpret the nature of your problem, and that would completely change how you use your metrics. So that's a very important thing to keep in mind when you're choosing your metrics. And they help with that with their fingerprint, problem fingerprint. Um, And so they have a list of different pitfalls. So here it's more about the problems, the formulation of the problems, and then they have pitfalls on the metrics. So you can have problems with the implementation of the matrix. You also have to be careful where you take your matrix from, if it's a package that someone just coded but hasn't been validated. So they have this Monai project that is very, it's enormous. They have loads of metrics. And I think they did something specifically with the Matrix Reloaded, the consortium. And yeah, they list all these pitfalls. It is a very, very big paper. They also show some examples of uses where they explain what kind of problem it is, what kind of metrics they should use to illustrate their findings. And I think I'll finish on one paragraph in the discussion, because one thing that is also important to keep in mind is that these metrics, you need to choose them wisely, but that's not the end of your process, because then to actually validate the results of your machine learning models, you need to make sure that they apply in real life. And even if you have the best metrics, you still need to validate them with, for example, a clinical validation on top of your metrics, because otherwise you can never know if it actually applies to the real life. Because especially in these domains, because we're not dealing with just numbers. We are trying to help patients and people in general. So you can't just have a couple of numbers that say, oh yeah, your model is working 90% of the time. So what happens with the 10% remaining? So on top of these metrics, we need to implement clinical validations or real life validations to our models. And I'm really happy that they say that in the discussion, because this is a very important aspect. So yeah, this is a massive paper. They have an online tool that they made freely available. So and they plan on updating it. So I think this is a very, very good initiative, and I hope people will use it. One small thing is that it's still a little bit complicated for some things, like some of the questions that they ask to refine your problem fingerprint. Sometimes it's a little bit tricky, but they give a lot of documentation on the side to decide what you need to do. But otherwise, it's a great initiative, and it's very comprehensive paper. So that's all for me. If you have questions.
Thank you, Chris. That is such an exciting paper and a lot of work. You sound like you played around with the online tool a bit. Am I right in assuming that?
Yeah.
How intuitive is it, and how readily does it apply to, for example, our domain?
It is a well, it is literally a survey. Well,
Mhm.
actually, can you see the website?
Yes, great.
Right. So um yeah, so you have, well, I finished the I finished the survey. But you have different steps, and they ask you different questions, and you have little like tooltips with if there could be an ambiguity, like to choose between option one or option two. They will have some explanations. And there was a couple of places where I was not entirely sure. but they also give references. So if you're, I mean, if you're in the process of making a research tool with machine learning, you can spend time to go in the resources and make sure that your problem is correctly formulated. But it is pretty simple to use. The questions, I did that like 10 minutes, and then you have a list of advice and some performance metrics. So I was glad to see that for my project, I used the two complementary metrics that they advise. It's just this one I didn't know about it, but that's cool because they also give you explanations like that. So that's for this one. And it's really nice, summarized. They give you like visual examples. It's really well made.
Wow. Just creating all this material must have
Yeah,
taken.
it's absolutely mad the amount of work.
The other question I had for you is obviously nowadays we can pretty much do anything with AI and machine learning. But do we know what's going on under the hood? So they provide references, so it's already quite transparent in comparison, I guess, to other algorithms out there. But do you see what's going on under the hood, or is it still a black box and you rely on
So they actually to choose the metrics or on the algorithms, you mean?
both?
So to choose the metrics, their whole process is completely open. They also they have the whole paper with the supplementary material is 211 pages. And they have figures for every single thing that they put together. They explain the whole process to choose the classes of the problems, the choice of the matrix. They have like it's. I think it's very, very transparent. I didn't go through the whole supplementary material because I wouldn't have had enough time in the weekend to do that. And also they have another paper that is, I think, pretty big as well. Yeah,
That's the sister
120.
paper you referred to in the beginning, right?
Yes, yeah. So yeah, uh it is quite transparent. You have loads of information, references, and yeah, in the on the website, they have references, and they give you the references of the metrics that you're using, for example. So if they tell you you should use the Hausdorff distance, they give you several references for the Hausdorff distance in the website. So that's pretty good. And for the algorithms, that's out of the scope of the paper because they explain the classes of problems and of algorithms, but they don't say which algorithm you should use. But the algorithms, how transparent it is depends on the model. You have some models where you can look into the weights and make kind of sense of it, and you have other models where it is more complicated. So yeah,
It's like an advanced dynamic statistics book. Just had this discussion yesterday with a colleague that we have come a long way. Like my generation still learned statistics from a book, and then he already learned it through YouTube tutorials, and now we have interactive websites tailored to your individual problem. So that's amazing. Lilith, you have a question as well.
Yeah, thank you, Chris, for this paper. It's a beast, as you said. But it's just maybe a bit of a futuristic question. So we have ChatGPT, right? But the sort of problem of ChatGPT is that we still have to tell what to do to solve our problem. I have an impression that this one, if you combine with those models like ChatGPT or that creates code, is basically you say, okay, I want to, I don't know, cure a patient, and then that thing will decide which metric to use, which model to use, appropriate to your problem, and then write the code, and the only thing that you have to do is find the power servers and like push the button. Is it do you think is it possible?
Oh, well, I think it will be possible in the probably next few years. There will be some situations where we could do that automatically. I mean, for now, I've been coding with large language models for a while now, and they still make a lot of mistakes. So
Oh, yeah.
I wouldn't trust it completely. But I mean, I would say you don't really need a large language model to code the entire thing, because you have a lot of packages that streamline the process of creating machine learning models. And sometimes you have like straight up tools that you can use, and they provide you with the algorithm, and you just input your data set. But in that case as well, if your problem might be slightly different from what was intended with the algorithm at the beginning, so you might want to choose your metrics as well. And that, for now, I don't know if a large language model could do that. Even though they have good advice on machine learning, especially because it's the kind of thing they've been trained on. But yeah, it will be possible in the next few years, maximum a decade. A lot of problems we will be able to do that without coding, really.
Yeah, because this website is sort of goes like on the more conceptual level decisions. So while ChatGPT is more execution,
Yeah.
the way I feel it, and this one is more goes in onto conceptual level. And I feel like at some point we don't need any more data scientists. So okay.
That's a scientist, yeah. That's potentially yeah, we'll have to update. Yeah, yeah.
Okay,
Well,
okay.
we're still not there, Lilith. Someone still has to make the final call, and that goes beyond what machine learning
Yeah,
algorithms are currently telling us.
yeah.
A lot of
Let's
instances.
hope. Thank you, Chris.
I think Eduardo was first.
Yeah, thank you, Chris. And see, yeah, my question is more a challenging question, and it relates to what Lilith and Stephanie just said. And it's so as you said at the end, we still need a clinician to check the images. So one may ask, what's the point of these models, and what would you say about this?
Well, it depends on the it depends a lot on the model, because some models, if you were trying to segment cells in microscopy images, it would take ages just for one image. So you're not even talking about several images. So there are some tasks that are literally impossible to do with humans. And for all the tasks, we see that the machine learning models are getting better and better at detecting objects, finding very subtle differences in images, to the point where a human couldn't see it, even experts. So in some domains it might take a little bit more time, but in the end, on a specific problem, that would be difficult to perform better as a human than a machine learning model that has specially been trained to do that. So at some point, we won't be able to compete on these specific problems with a machine learning model. But that doesn't mean that humans are going to be useless even for these problems, because yes, we need to make sure that they are not doing the wrong thing in the end. So I think we will have to keep a balance between training models and validating them, because for now I think that's why they had to make this paper, because we see in the community that loads and loads of papers come out about for example, I was doing lesion segmentation, and just on stroke segmentation you have dozens of papers, but not a single one of them can be used in clinic. So that's why they are trying to improve that. But still, we will need humans at the end to validate the results, at least for now.
Okay, thank you. Wait, I was wondering if you would also need humans in the future to generate data to train the models, or if do you think the data will be available anyway to?
Well, it really depends on the problems. Again, there are some problems where humans, I mean, for large language models, for example, because the goal is to simulate, well, for some people, the goal is to simulate what humans are doing. You need humans' inputs to fine-tune the model to be better at doing that. But for some other problems, you also have models that can create synthetic data that can help with the training more models. But again, we need humans to decide, is it too much? Because if you only have synthetic data, how does it relate to real life anymore? You need someone in the loop to make sure that it's still relevant.
Sabrina, final question.
Okay. Thank you, Chris. Really interesting, this paper and yeah, your presentation. So one of the point is, yes, that we should use different types of analysis. Okay, it's fine. But I was wondering about the dice coefficient, because we know it was used a lot in the past. So I would think if they explain it now, when could be still a good analysis. So when could be still good? I don't know if they explain the situations.
Yeah, so if your problem is more interested in capturing the amount of overlap between your target, so your ground truth, and the prediction of your model, that's exactly what DICE is doing. So in that case, DICE is very relevant, but that would be a very narrow problem, because if you have the slightest other object in your image that you're trying to detect, DICE won't be good at finding that out. Or determining if your model is capable of finding that out. So it really depends on your problem. But if your problem is slightly more complicated than just the overlap, that doesn't mean that you need to discard the DICE. That might mean that you need DICE and another couple of measures. And for example, the example that I showed that I ran through their website is for lesion segmentation. And I'm really interested in finding the overlap, the amount of overlap between my ground truth and my prediction. But also, I want to make sure that it's capturing all the lesions in the brain. So I also used the distance, because if my model is missing some spots of lesion, the distance is going to greatly increase compared to my ground truth, because it's missing these points. And that's something that the DICE wouldn't capture. So when I'm evaluating my model, I will look at both. I won't say, oh, I have a super good DICE, but if the distance is like dozens of voxels, my model is trash. So yeah, complementary matrix is the key here.
Yeah, clear. Thanks.
Thank you all. We are way over time today, but I didn't didn't want to cut this discussion short. So thank you very much for jumping in and presenting this paper. I think it was very well presented and understandable, despite being very comprehensive and complex thematically. Thanks a lot. Next week, we're going to have Eduardo present, and I wish you all an exciting week in science.